And welcome back to the 11th episode of The Marvelous World of the Galaxy. In this one, we are going to take another couple of steps up the ladder of scale, and we will look at the largest structures in existence, starting with galaxy clusters and galaxy superclusters. And after that, we will take the next step and final step up and look at the large scale structure of the universe itself. Galaxy clusters are, well, clusters of galaxies. They are, as you can say, they are like galaxy groups, but a little more wow. So galaxy clusters, as you can see in the table over here, have a core radius that is similar to that of galaxy groups. A slightly larger characteristic or scale radius, and a velocity dispersion that is much larger, which of course also reflects the much larger mass in the cluster compared to the group. Groups contain typically a few tens of galaxies, while clusters contain hundreds and sometimes even thousands of galaxies. So galaxy clusters are the largest bound structures in the universe. That means that they're the largest structures where the internal or the mutual gravitational pull is stronger than the general expansion of the universe, means that even as the universe as a whole expands, clusters will stay together and retain their structure, retain their shape and size and general mass density, which is not the case for any structure larger than galaxy clusters. Galaxy clusters live at the intersection of dark matter filaments, as we have talked about before. Dark matter is not evenly distributed in the universe, but is distributed in this like sponge-like structure where we have large voids with very low matter density, and around them are these kind of walls with slightly higher matter density. And as these walls are meeting, we get these strings or filaments with even higher matter density. And where these filaments meet, we have these knots or node points, which are then the points of the very highest matter densities. And galaxy clusters live along these filaments, and at the intersections of these filaments, we find the most massive galaxy clusters. Galaxy clusters are excellent places to study environmental effects on galaxy formation and evolution, and that is simply because galaxy clusters are just so full of environment. Like galaxy clusters are super dense, have a very high mass density, they contain a lot of galaxies, and they contain a lot of intra-cluster gas. So there is always something to interact with in a galaxy cluster, which means, of course, that environmental effects are sped up dramatically in a cluster compared to out in field galaxies, where environmental effects are extremely slow. So we can study them in much better detail in clusters than we can outside of clusters. So here is an observed map of the large-scale structure that I talked about before. This is made with the dark energy, or made by the Dark Energy Survey, and this is millions of galaxies that have had their position on the sky and their redshift, and hence their distance from us measured. And as you can see, you see exactly what we described before. There are these voids, and then there are these filaments, and where these filaments meet, we have these extra strong overdensities, which is where our clusters and superclusters live, and they are very easily seen in this map. Here is basically the same structures, but this time in a simulation. This is the so-called Uchu simulation, which shows only dark matter here. So basically the brightness and color here just reflects the dark matter mass density at a given point. But we can see that there are these large voids, right? And there are these large overdensities where we have extremely large, massive clusters. So this here is just a zoom in of this over here. And we have even more of a zoom in. Here you see a 10 megaparsec scale is this bar. So this is a few tens of megaparsecs across, which means, yeah, that's what we see down here. Here we are down to maybe 6 megaparsecs across in the very central core of this. And in here, we then see the very, very central core of the central half a megaparsec of this cluster. And what we see here is the brightest cluster galaxy, right? The CD galaxy, surrounded by a lot of other galaxies in the densest core of the cluster. And then we see in like at larger distances how it is connecting to filament and other clusters of galaxies with dark matter overdensities. Down here, by the way, we have a Milky Way-sized halo just for comparison. So as you can see, a Milky Way-sized halo would be shown as maybe one of the average size galaxies here, with this very bright central galaxy here being many, many times larger than a typical L-star galaxy. Galaxy clusters consist of a few main constituents. The first one of them, of course, is galaxies. What we look at here is the so-called Pandora's cluster, as it was observed with the James Webb Space Telescope a couple of years ago. Here, so in optical imaging, we're used to seeing these early type galaxies as reddish-orange galaxies. In near-infrared imaging, as we see here with the NIRCam, these galaxies have a tendency of showing up white. So any of these white fuzzy blobs that you look at here are cluster member galaxies. And if we try to zoom in on this extremely fantastic image that we have here, we can see a lot of glorious detail. First off, we can see that there are gravitational lens galaxies, practically speaking, everywhere. Right? Here, 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 here. Once you see them, you can't stop seeing them. Here, 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 here. They're everywhere. So this is really a fantastic time to be a researcher in gravitational lensing. We can also see something else, right? We can see this galaxy here, which clearly is an early type galaxy, but which clearly also contains some shells or maybe even the remainder of a disk structure here. It is hard to see whether it's a shell or a disk, but it's definitely some kind of substructure, right? We see something that looks like some lenticular galaxies here, right? They're not really spirals, but they definitely look disky. We see some very beautiful spiral galaxies, for example, here and here, although there aren't a lot of spiral galaxies in a cluster, as we will get back to later. One thing that is really cool to look at is that if we look at this one, which very well might be the brightest cluster galaxy and therefore also the CD galaxy, we can actually see that there is this large halo of stars around it, right? And in this halo, if you look at it closer, you can see that there are these little dots. And I don't know, I would immediately think that that was probably just an artifact or something, but it is not. These are actual globular clusters in the stellar halo of this massive, massive early type galaxy. So yeah, again, this is just a little bit of going ooh and ah at some really shiny images, because we can see so much. And by the way, this cluster is actually only a detail of a much larger cluster, or rather a much larger complex of galaxy clusters. There is a twin cluster plus, I believe, if I remember correctly, also a smaller third cluster that is part of like this conglomeration of galaxy clusters. By the way, this work that has been done here, this Uncover collaboration, has had some active members from here in Stockholm as well. I'm not personally one of them, but we definitely have had a couple of them in the group. On top of the galaxies, there's also what we call the intracluster stars, which are stars that are not part of any particular galaxy in the cluster, but rather are making up like a sea of galaxies in the general gravitational potential of the cluster. What we're looking at here is a very special imaging technique, or rather image processing technique, where for most of the light we just image things like they normally are. But once we reach the limit of the border between almost no light and completely no light, we switch from black to white again. So where you can see there's consistently black background, that means that there is an ever so faint stellar population present. And it is only when we get out in the corners out here, when it gets completely white in the background again, that we can know that there is basically no light. So what this gives us is that this is a fantastic way of, at the same time, showing the detail in the galaxies individually, while also mapping these like really, really faint structures, this really faint sea of intracluster stars in this cluster. This is a technique that, by the way, has also been partially developed by a former postdoc here at Stockholm University, Nushka Chamba, who has worked quite a lot with this. She has later moved on to NASA in California. On top of intracluster stars and galaxies, we also have hot intracluster X-ray gas. This is exactly the same as we also have in early type galaxies, just on a larger scale. And it is the exact same mechanisms that heat it up and make sure that it becomes luminous in X-rays. And as with early type galaxies, we can look at the center that it is actually quite dense and it is quite luminous in X-rays, which also means, of course, that it is quite efficient at cooling galaxies, which means that the cooling time in the center of a galaxy cluster is actually significantly lower than the Hubble time, or the current age of the universe. But there isn't really any star formation in the center of these clusters, so there's got to be something that heats up the gas again, because if it just cooled, it would condense into neutral gas and spark new rounds of star formation. But this basically doesn't happen. I mean, it happens a tiny little bit, but it basically doesn't happen. Out in the outskirts of the galaxy, on the other hand, the gas is much less dense, it gets much less luminous, and here the cooling time out here is typically larger, and oftentimes much larger than the current age of the universe. And finally, we have, of course, the largest amount of matter in galaxy clusters, which is dark matter. What we're looking at here is the same kind of map that we have looked at before when we talked about the bullet cluster. This is a map of the distribution of dark matter in a galaxy cluster as mapped by weak gravitational lensing of background galaxies, where we've basically done the statistics on the stretching and the direction of the way the galaxies are stretched, and by those means have been able to map the dark matter distribution in this cluster. But one thing that is really cool about this compared to the bullet cluster, I think, is that we can see here that we now have so good observations and such good statistics that we don't have to see the dark matter distribution as smooth and like smeared out, but we can actually see structure in the dark matter distribution. And we can see that this is not just like a smooth, one big smooth distribution, but there is indeed substructure in it. We can see that there is this core in the center, right? But then we can see that there's this ring that is kind of underdense before we get even further out, where there is another ring, which is again an overdensity of dark matter. So this shows us that this galaxy cluster is not a relaxed and not a virialized structure, right? This is a structure that is still in the process of forming, relaxing, and settling down into an equilibrium. It is quite far from being in equilibrium at this point. And I think it's quite interesting that you can see that we've reached the point where we can see that simply because we have gotten better and better observations, better and better instruments, and better data analysis techniques. This is something that has only been possible to do for maybe 10, 15 years or something like that. From this, we can also see that the mass to light ratio in galaxy clusters is much higher than it is in individual galaxies or galaxy groups. In individual galaxies, we typically have a mass to light ratio of similar to or less than 25, especially in spiral galaxies and star-forming galaxies. This ratio gets even lower, right? We have already done some exercises with this. When we look at galaxy groups, it gets higher because there is dark matter in the general potential gravitational well of the group, but we still have a mass to light ratio of maybe 100. But once we get to the scale of cluster, these effects get even stronger, and we have a mass to light ratio of 200 and up to 300 compared to in only like 10 or a few tens in single galaxies. And actually, for galaxy clusters, these values start to approach the general cosmic mass to light ratio in the universe as a whole. Galaxy clusters can have cool cores or not cool cores. As we looked at before, clusters, the very central parts of clusters are quite dense, quite luminous in X-rays, which means that they're quite efficient at cooling down. So we can use the existence of a cool core basically to infer that this is a galaxy that is closer to, or this is a galaxy cluster, sorry, that is closer to equilibrium, closer, has had longer time to settle down, and has had longer time for its core to cool down, but has not really had anything that would reheat it effectively to the same temperatures as in the outer parts. We can see that over in panel B here, where we have two different galaxies in all four panels actually. You see here that the dashed curve is a non-cool core galaxy cluster, and the fully drawn curve is a cool core galaxy cluster. And what we see is that the temperature in the cool core galaxy cluster is a good deal lower than it is in the outskirts, right? It is definitely significantly lower, but we can also see that it is no more than a factor of maybe 2, maybe a bit more if we get even further into the center. It's cool, but it's not like much cooler. It's not like orders of magnitude cooler like it would have been if we had the gas like condense into neutral gas again, and even molecular gas and starting to form stars. This is definitely not happening. We do know, however, that these galaxies have a temperature profile, or these galaxy clusters, sorry again, have a temperature profile that grows with radius, increases with radius. Their cooling time is shorter than the age of the cluster, which means that they have had time to cool down, but also that they have not recently been undergoing any mergers. And when we see mergers here, we mean mergers between clusters, galaxy clusters, not mergers between individual galaxies. They have a higher central gas density, again, because it has had time to cool down and settle down. And these cluster also has regular shape, again, reflecting that they are closer to being relaxed, virialized systems. In contrast, we have the non-cool core galaxy clusters, which is the dashed ones here. And again, if we look at the temperature, we see that the temperature curve is essentially flat. We also see that the central density is lower than in the cool core galaxy, as we can see here in panel A. And we can see in the cooling time that the cooling time is much larger. It is close to being around a gigayear or even more in the outskirts, which is much more comparable to the formation time of a galaxy cluster, and therefore the probable age of the cluster itself. These are typically clusters that are undergoing mergers or quite recently have been undergoing mergers. They are irregular in shape, and again, as you can see up here, they have lower gas density in the central regions in the core. When we want to look for galaxy clusters, one very useful and efficient way of finding them is the so-called Sunyaev-Seldovich effect. This effect is what happens when photons of the cosmic microwave background traverse through the hot intracluster medium in a galaxy cluster and undergo what is called inverse Compton scattering. Means that they bounce off of the electrons, are briefly absorbed and then re-emitted. And what then happens is that because these electrons typically have very high energy, a statistically significant fraction of these photons end up coming out with a higher energy than they had when they came in. So what that means is basically the entire spectrum of the CMB, when seen through such a cluster, has higher energy than it had before or than it has in the surrounding areas when we look at it, which means that in a certain sense, this is seen as a hotspot. However, actually, we often in practice see it as a cold spot. And why is that? Well, we can take a look at the right panel over here. So this panel is a graph over the effect of the Sunyaev-Seldovich effect on the temperature of radiation. And what we see is that for photons with lower frequency than around just 218, I think, gigahertz, it is actually going to go down. The intensity of the radiation is going to go down. If we look at the left graph here, we can kind of see why. Here we have a probability distribution of photon energies, and we can see that because all of the energies, statistically speaking, have gotten higher energy, this energy or this distribution has been pushed towards the blue side of the spectrum. But if we look at lower frequency parts of the spectrum, basically below the value that we see here, then we see that the Sunyaev-Seldovich effect has actually lowered the intensity of radiation at these frequencies, right? So if we look at frequencies that are colder than this, and the peak of the cosmic microwave background is around here, right? So if we look at that, we can see that we actually will see the cosmic microwave background through a galaxy cluster as a cold spot in the cosmic microwave background rather than as a hot spot, simply because we only look at the parts of the spectrum over here where there are fewer photons because they all have gotten larger energy and have been moved over to the bluer parts of the spectrum. So that way, the Sunyaev-Seldovich effect actually causes the brightness temperature of the CMB to go down at the peak of at the peak frequencies of the CMB, and therefore we see it as cold spots rather than hot spots. So if we look at this, and if we have sufficiently good measurements, which we have more and more often, we can spatially resolve the measurements of this effect, and that can allow us to map the gas pressure, that is the gas temperature inside the cluster. And if we now assume the temperature to be constant, then the integrated temperature offset can be used to determine the gas mass of the cluster. So basically, we assume this number here is constant, then this integral here only depends on the number density. And if we have measured the effect of the Sunyaev-Seltovich effect over here. We can rearrange and we can use this measurement and the assumption of this constant temperature to find the number density and the integrated number density, and therefore the gas mass of the cluster. And as we saw before, this assumption of a constant temperature of the gas is actually not a bad one. It might be off by a factor of 2 or even 4, but it still gives us the right order of magnitude of the gas mass of the cluster, right? We still know within a factor, typically a factor of 2, what the gas mass is. The environmental impact on galaxies. I mentioned before that galaxy clusters were a brilliant place to study the environmental impact on galaxies. And we have this thing that is called the morphology density relation, which you can see here. What we see here in this plot here is basically a map of coordinates of galaxies in a galaxy cluster. Well, maybe not all of these galaxies are actually cluster members, but quite a few of them, or the majority of them definitely are. The green contours, as you can see, is X-ray gas. Main part of the hot X-ray gas is found in the general gravitational well of the cluster itself, but you can see that there's also some X-ray halos of other early type galaxies, individual early type galaxies sitting around here. Then we have the number of ellipticals or individual ellipticals in red, and individual spiral galaxies in blue as stars. And as you can see in the very center of this galaxy cluster, the elliptical galaxies completely dominate, whereas the distribution gets way more even out in the outskirts of the cluster. Here we have a graph where I am very sorry, have cut off the description of what is on the axes out here and out here, but it is figure number 613 in the book. Here it is. And here we can see that what we have out here is the number of galaxies per 0.1 magnitude bin. So that is what we see on each of the small individual y-axes in each of these panels. And on each individual y-axis over here, we see the colors, the U minus R colors of galaxies. So this is basically a color distribution function of galaxies at a given density and at a given luminosity. So these panels are arranged by decreasing luminosity as we go down here and by increasing density as we go to the right. And what we can see is that at low density, generally, especially at low density and low mass, the bluer bump here. So everywhere we have this two double peaked distribution, right? But the relative strengths of these two peaks is very different in different environments. So in very dense environments, we can see that the red peak is much stronger than the blue peak, reflecting that early type galaxies are much more common in very dense environments than they are in very sparse environments. We can also see that the blue peak is much stronger, relatively speaking, at low luminosities compared to high luminosities, reflecting, of course, that the very highest luminosity galaxies are elliptical galaxies simply because they are much larger. We can also see that there is a large area here in the middle where the distribution or where the relative strengths is much more evenly distributed. But spiral and irregular galaxies are almost non-existent in the center of galaxy clusters, is what we can perhaps most importantly take away from this graph here. And this is because of three main effects, environmental effects. that we're going to talk about. These are ram pressure stripping, galaxy strangulation, and galaxy harassment. We have a beautiful poetic language to describe what is going on in the universe in the astrophysical community, and it gets even better. Anyway, starting off with so-called strangulation, also called quenching. This is what happens when galaxies fly by each other, not too close, not so close that they perhaps disrupt each other's shape in a major way, but the gravitational force can still remove the circumgalactic medium around the star-forming galaxy if it gets close to an even larger elliptical galaxy. So what happens then is that, as we talked about before, star-forming galaxies form stars when they can accrete a lot of gas from the surroundings onto the disk, can fall down there and spark new generations of star formation, right? But if some other galaxy by its gravitational force has removed these surrounding reservoirs of neutral gas, then there's not going to be any future star formation because there is nothing that can be accreted onto the disk. So that way, the these star-forming galaxies will simply just slowly cease to form stars and become early type galaxies. This is a rather slow process, but it is definitely efficient. The next one is ram pressure stripping. This is when a star-forming galaxy is kind of falling into the gravitational well of a galaxy cluster. And as it is rubbing against the hot intracluster gas, which kind of sandblasts the neutral gas, the cold and neutral gas, and dense gas around these galaxies away from them, strips it off them, and leads to this phenomenon called jellyfish galaxies. Jellyfish galaxies are called that because, I'm going to illustrate again, as they fall down into the gravitational potential and are blasted by this hot intracluster gas, it will strip the neutral gas off, and it will hang behind these galaxies in threads. And these threads will often have star formation sparked in them, so they will hang in like these glittering threads behind them, looking a lot like tropical jellyfish. Then we have the so-called harassment or tidal stripping, which is similar to strangulation, except that these are closer encounters of galaxies. So these are close enough that these galaxy encounters can slowly remove parts of the actual stellar disk of a star-forming galaxy, and that way, of course, also removing large parts of the gas that is already in it, not just the surrounding reservoirs for future star formation, but also a lot of the gas that is already sitting in the disk. So this is basically like a more rapid, more efficient version of the strangulation/quenching. And finally, we have dynamical friction, which we have already talked about, which is where the galactic motion through this sea of stars and dark matter particle is transferred into stellar motion, which will cause a larger and larger probability of galaxy interaction as a galaxy is spiraling in and settling down into the core of the cluster. And as it does that, it has a larger and larger probability, as mentioned, of interacting with other larger galaxies in a process that we call galactic cannibalism. I told you we have a beautiful poetic language in astrophysics. So to summarize, galaxy clusters are enormous gravitationally bound overdensities. They are the largest gravitationally bound structures that exist. They have total masses of 10 to the 14 and up to the 10 to the 15 solar masses, typically. They contain dark matter, they contain galaxies and intracluster gas and intracluster stars. The dark matter to baryonic matter ratio is similar to the overall value of the cosmos, the overall value of the universe, in stark contrast to individual galaxies where the baryonic matter is way more prominent than in the cosmos as a whole. There are many more elliptical and early-type galaxies in galaxy clusters than there are outside of them, or in the field as we call it. Clusters have a hot intracluster medium, and it is X-ray bright, and oftentimes it is, or actually all the time, it is still heating up. Even in cold core clusters, there is some mechanism that heats up the central parts of the galaxy. The galaxy's gas content is a very strong function of the environment. We have seen how the environment can strip dense gas off of galaxies and basically just like blow it out in the broader intracluster medium of a galaxy cluster. And that is something that happens over relatively short time spans inside of clusters. Clusters are not yet, or mostly not yet, fully relaxed and fully virialized. They are not in equilibrium. Typically, cluster formation is an ongoing process, and typically clusters are asymmetric and velocity distributions are non-Gaussian. So unlike the typical early type galaxies, which is very often actually in equilibrium, is relaxed and virialized, the typical galaxy cluster is not relaxed, not virialized, and not settled down into any kind of equilibrium. That was it for the first half of lecture 11. I am happy and thankful you stayed with me this long, and I will see you in the next one.